Continuing education knows that at the end, students want to graduate, and we can help them do that because we take the time to really listen to their needs and we understand all the different options that are available across the campus for them.
We don't take a cookie cutter approach. We realize each student comes with their own story. So whether it's a part-time student looking to complete a degree program or someone just looking for online courses, we're there to connect them to the resources of the university.
April 14th. It is 9 o'clock, and my name is Sam Weaver. I'm the moderator for this panel. And the panel today that you're going to hear is Energy Technology That Will Power the World. Before we get started, I would like to read a land acknowledgement. I would like to acknowledge that Boulder is on the ancestral homelands and unceded territory of indigenous people who have traversed, lived in, and stewarded lands in the Boulder Valley since time immemorial. Those indigenous nations include the Apache, Arapaho, Cheyenne, Comanche, Pawnee, Shoshone, Sioux, and Ute. And one other thing I'd like to mention today is that we want to make sure that you all in the audience have a chance to ask questions, and here's how we're going to handle the Q&A, which will be in the last 20 minutes of the panel. We're using a note card system this year to receive questions from the audience. At any time in the session, simply raise your hand, and we have people who are helping produce the session who will come and give you a note card and a pencil from one of our producers. If you could please write legibly, and also if you could please indicate whether you're a student at CU or some other institution in Boulder or not, because we'd like to prioritize student questions. When you finish writing your question, raise your hand again, and the producer will come back and take your card and your question up to us here. And please make your questions brief and to the point so that I can read them clearly. I'll give you a quick background for me. I was on city council here in Boulder for 8 years, mayor for 2, and in my day job, I work on clean energy. I've been working on clean energy hardware for small-scale power generation since 2006. And now I would like to introduce our panelists who we'll be hearing from for the rest of the morning. First, we have Kyri Baker. Kyri is a professor here at CU Boulder. She graduated from Carnegie Mellon with the Grand Slam, bachelor's, master's, and PhD. She was at NREL for 3 years, and she's a specialist on how to analyze power grids. Next, we have Peter Green. He's the Chief Research Officer and Deputy Lab Director for the National Renewable Energy Labs. He graduated from Cornell, spent 10 years doing work at Sandia and 20 years in academia. His specialty has been chemical engineering within materials science, and he has been a professor at the University of Texas at Austin and University of Michigan. And we also have Peter Kelly-Detwiler to my left here. Peter is an energy consultant to utilities and independent power producers, and he is the author of a fantastic book on the energy transition called Energy Switch. And finally, we have with us Emma Redfoot. Emma is a nuclear engineer and a site lead for Oklo, which is a nuclear power company, and she is also on the board of directors for Mothers for Nuclear Power. She has a BA in environmental studies from Lewis and Clark College. And so with that, we're going to kick off and have each panelist take 3 minutes and tell us a little bit about their background and what they think about the subject of today's conversation and how their background leads them to take that position on the energy technologies that are coming and will affect us all. So with that, I'm going to turn to Kyri Baker for 3-minute introduction and comments. Kyri.
Okay, thanks, Sam, and thank you all for joining us here today. As Sam said, I'm a professor here at CU Boulder in engineering, and I study the power grid, how buildings and consumers can better interact with the power grid, and issues of reliability, resiliency, and how renewable energy can be better integrated into the grid. So what makes me interested in this topic is sort of the idea that energy is now touching all of our lives, average consumers that previously just flipped on a light switch and didn't have to think at all about what was happening at the power grid. Now consumers are being called on to reduce their consumption, change their thermostat set points, decide when they charge their electric vehicle. It's really a topic that's addressing all of society. And so it's becoming important, and it's becoming very, very interesting from a technological point of view. So as an engineer, I'm thinking about how can I use my skill set to improve the lives of millions of people? And so the way that I think about that is not only, improving things like battery technologies, improving the efficiency of solar panels, improving the efficiency of wind turbines, but also from the systems perspective, how do we integrate everything and match supply and demand? Because, this is actually a very, very complex engineering problem. Electricity is delivered to us 60 hertz in the United States, meaning the AC waveform is going up and down 60 cycles per second. Generators are producing power at this frequency. If we don't match supply and demand at a sub-second level, we get lights flickering, we get large-scale blackouts. So it's a complex engineering problem, which makes it super interesting to me. So that not only takes things like traditional power plants, but also things like energy storage and things like coordinating demand and coordinating when people do things like charge their electric vehicles. So that's what makes me interested about technology, and I'm really happy to serve on the panel.
Very good. Thank you very much. And to your point, somebody has once described the electricity grid to me as the largest machine that humanity's ever built, which I think is a neat perspective. Thank you for that, Kyri. Next, we have Peter Green. Peter, give us a little background on what you think about the subject.
Yeah, good morning, everyone. I'm delighted to be here. I first became interested in this topic many years ago while I was a professor at University of Michigan, and where I led a large group of faculty across the university doing very basic research on solar, and it's another area of thermoelectrics, which most of you haven't heard of. It's about conversion between heat and electricity. A year later, I was in Africa teaching a course on energy materials with colleagues from around the world. And at that point, I said, you know what, I can make a bigger contribution. And so I left Michigan and came to NREL. Right? So when I think about this topic, as a scientist, I'm forced to go back and look at things at the beginning, right? You remember the Model T Ford? That was the beginning of sort of a massive production of that vehicle. It displaced the EVs, by the way, at that time, and largely because there's cheap oil. We went from there to build an infrastructure: steel, concrete, ammonia for fertilizer. And, for example, steel, for every ton of steel you produce 1.3 tons of CO2, just to give you an idea. So we continued along that path. What was interesting is that years earlier, before the Model T, there was a prediction that the emissions of CO2 would eventually warm the planet. And the reaction was, no, let's not worry about it. But what they didn't predict was that at that point, 6 billion people would show up on the planet since then. And each of them uses 3 times as much power as they did, and it's all fossil. And to make matters even more complicated, to really make your morning, we started making plastics in the 1950s. And the weight of all plastics that have been synthesized to date weighs more than all humans who ever occupy this planet. So that's another challenge that's sort of compounded. But now we are with the climate issue, the extreme weather events, 10 times as significant as they were 20 years ago. They're not going away, the new world we're looking at. But getting back to the technology part, which is exciting, right? Late 1800s, we discovered X-rays. Why is that important? We learned about the structure of matter. Later on, we developed semiconductors. We learned physics. We learned all these kinds of things, and we built this massive microelectronics empire. The good news is that that's why we've got solar. That's why we have technologies like wind. All these things are now potentially available. So the toolbox exists for us to solve this problem. And it's not just a technical problem. It's not just a scientific problem. It's a social problem, right? We're going to have to meet people where they are and make sure that they're part of this transition. If we don't do that, we haven't solved the problem yet. So we're going to have to be seriously honest about when we develop technologies, we need to understand how to apply them, where they're going to be applied, who benefits, and make sure that it's a just transition for everybody. So that's sort of my beginning. Thank you.
That's great. Thank you, Peter. And next we'll turn to the other Peter on the panel, Peter Kelly-Detwiler. What do you think?
Thank you. So my background, is this working
There
okay? I've been 30 years in the power industry. I used to head up Constellation Energy's demand response group, where we paid people not to use electricity during periods of peak demand. It'd be like building a virtual lane on the highway and paying people to drive before 6 in the morning or after 10 o'clock, so avoid rush hour. So I used to be a doer, and then in 2012 I left Constellation. I started writing for Forbes and other publications, and I stopped being a doer, and I realized over time that this was a really complex systems of systems problem that we were trying to solve here. And I also realized that because it's so complex, the narrative becomes critically important. And so ultimately, I've defaulted into becoming sort of a storyteller for the industry. So I mentioned in another panel, I read 2 to 3 hours a day. I have 32 newsletters. I teach 7-hour classes on hydrogen, distributed energy resources, batteries and electric vehicles, batteries and storage, electric vehicles, and then fundamentals of the grid. So I have 2,200 URLs, and I'm always trying to figure out, like, what's the next thing that's going to move the needle, that's going to change humanity within the context of the 3 major drivers, which are decarbonization, that thing we have to do, decentralization, which is the move to more and more of these technologies out to all of you, to the grid edge, and it's not just electricity, it's other tech as well. And then digitalization. How does the proliferation of bits and bytes change the world we live in and inform us as to how we can do this more and more efficiently? And the grid and now our energy economy is really a cyber physical environment that we live in. We're attached to it in many ways. Certainly what you're doing with grid modeling is a classic example of that. And as we get the chat GBTs and the supercomputers and we start to harness more and more of that artificial intelligence, there is great potential to make better stuff, because the grid, for example, is all about physics and chemistry, and manage the stuff that we make better and more intelligently. So there's a great deal of hope there, because every time we open up the toolbox, the tools get shinier, many of them get cheaper, and they become more adaptable for the problems we're trying to solve.
Peter, that was great. I really like your insight about the 3 Ds you gave us: decarbonization, decentralization, digitization. That's great. Thank you very much. And last, we have Emma. Emma, what do you think?
Yeah, I'm happy to be on this panel. I'm glad to be with people like this that are working on solutions to one of the biggest problems that we're facing in the world, clearly, and we need decarbonization. So a little bit about me. I grew up in Montana. I grew up in a beautiful part of Montana and spent a lot of my time backpacking and snowboarding and outdoors, and realizing that, climate change is going to be one of the biggest issues of my generation. I went to school and got a degree in environmental studies. I went to Lewis and Clark College in Portland, Oregon, and got a degree in environmental studies. During that process, I lived on an organic permaculture farm on the coast of Ecuador for 6 months, and then I lived in Cusco, Peru for 6 months studying NGOs and studying volunteer tourism. So I went and talked to all these different NGOs about what they're doing to try to help people. And these NGOs were sometimes made up of people from the local Cusco area. They were sometimes from other parts of Peru, and they were sometimes from other countries. And what I learned from that experience is the people that make the biggest difference in their communities are people from those communities. So somebody from the United States coming to these different countries and telling them how to live their lives is not a good way to move forward. So from that experience, I also realized what it meant for people to live with very, very little energy accessibility, and how much, and from my environmental studies background, I knew that energy accessibility increased access to healthcare, access to education, women's rights improved, because then you have, more jobs, more opportunities outside of the home. So from there, I took a year, I read a ton of books about energy, and I decided that nuclear power really is an important part of our clean energy mix, along with other solutions out there. I decided that because nuclear has been proven to have deep decarbonization of industrial countries quickly. So countries like France, who deeply decarbonized very quickly, really used a lot of nuclear power. So it's a proven way for us to have an industrial country that has very few emissions. And the goal here is to have very few emissions. And also, I think, as was brought up already on this panel, we need so much power. We need to move, we need to electrify. We need, we need to replace transportation, all kind of process heat applications with more clean energy. So this is a big problem. And on top of that, a lot of the world needs more power. We can't reduce how much power is being consumed in the world, because a lot of people, their lives are going to get a lot better if they have more access to energy. And so because of all of those reasons and my research on energy, I went back to school and I got a master's in nuclear engineering. And since then, I've been working on advanced nuclear solutions. So thanks so much.
Very good. Thank you, Emma. And the things I got from that were the centrality of energy to people's lives, especially people trying to better their lives who are in poverty. And the other thing is that we need to talk about nuclear. And I'll just put in a personal note. My father was a nuclear metallurgical engineer with a PhD who worked at Oak Ridge National Lab. So I grew up talking about nuclear energy and energy issues at the dinner table. And so it is something that a lot of people misunderstand and is a conversation that is well worthwhile. So we're going to move into a phase where I'm going to ask the panelists some questions and then kind of see where the conversation takes us. And the first question I have is about storage. So gasoline is the wonderful thing that we use all the time in our cars, and it's so great because gasoline has two properties. It can generate energy to move the car, and it's the storage itself. And so the reason that gasoline and oil are so hard to displace is because they bring two things. They bring energy and storage together. Electricity is a different subject. We have to electrify everything to decarbonize, but it's hard to store because moving electrons is a transitional phenomena. So there's many technologies, lithium-ion batteries, sodium flow batteries, gravity, flywheels, hydrogen, and others that are approaches to be able to store electricity in some form and then regenerate it. So I'd just ask each of the panelists, what do you think some of the most important areas of storage technology research are, and how will we see it come into the energy systems that we interact with? And if it's okay, I'd like to start with Peter to my left, Peter Kelly-Detwiler, and see what your thoughts are on energy storage, electricity storage.
Sure. Without going into a huge treatise, there are a few key issues. One, the frequency we mentioned before, maintaining the grid at 60 hertz. Lithium-ion batteries are great for that. They're better than any other resource on the grid because they can follow the signal super fast. The challenge with lithium is it's not cost effective beyond, say, 6 hours of storage duration with today's costs. There are a lot of other technologies that haven't scaled to that size, but offer the solution or the opportunity to solve for longer duration storage. We talked yesterday on our panel about this thing called the Dunkelflaute, the German word for when the wind don't blow and the sun don't shine and your renewables aren't powering your system. You need raw gigawatt hours, terawatt hours of energy to solve that problem. The batteries we have today won't do that. And even the flow batteries that can give you 10 hours, they won't do it. Hydrogen potentially could if you stored huge amounts of hydrogen in caverns, but the efficiency losses of making that hydrogen and then storing it and putting it through turbines, you lose about 2/3 of the energy. So there are a lot of different technologies being researched. Another one, sodium batteries. They don't use lithium. They're starting to go into cars in China. You don't have cobalt, you don't have lithium. It could be cheaper. There's a lot of work still being done. Materials science is making huge improvements, but ultimately all these technologies need to face the bracing discipline of the marketplace. If they can't scale fast and find places to be cost competitive, they won't make it into the market, and that's the biggest challenge.
Great, thank you. Anyone else?
Yeah,
Peter.
so on the topic of hydrogen, so we're going to be using a lot of renewables on the grid, and hydrogen is going to be a key part of it. And we want to get to hydrogen via electrolysis, not the current process of the SMR process. And with hydrogen, there are many things you can do. You can capture CO2, and with the hydrogen, use a range of synthetic chemical techniques, biochemical or electrochemical techniques to make fuels, synthetic fuels, rather than you going the petroleum route. That's one thing to be able to do, for example. You have hydrogen, for example, to way of making up ammonia, synthetic, rather than going the petroleum route, as another example. There's the fuel cells, hydrogen fuel cells that are going to be for long-haul trucking, for example. When you have renewables and you have to store the energy, you don't have to. You can actually use renewables when there's excess renewables to provide the power for electrolysis. There's a lot of work going on right now And there's a goal to get to $1 per kilogram. It's a goal that people around the globe are collaborating on to get to that point. We're looking towards a hydrogen infrastructure, just like you have a natural gas infrastructure globally to get to it. So it's going to be a key part of the solution. Hydrogen is going to be a part of decarbonization of steel, the steel processes, which gives off so much CO2. It's going to be a part of the decarbonization of other industrial processes. It is going to be a key part of the future.
Kylie.
Yeah, so when I ask my students, you have a bunch of solar being generated in Hawaii, you have a bunch of solar being generated in California. We now have what's called a duck curve problem, where in the middle of the day, you have a huge dip in the amount of energy that you need to supply from other sources. And recently in California, we had such a dip that so much solar was generated, it was basically net zero at those time instances. So my question to them is always, what do we do about this problem? We have a ton of solar, but we need to shift that generation to the evening peaks to overlap. And their answer to me every single semester is batteries. Let's just buy a bunch of batteries. And so then I show them the cost of batteries, how we're gonna have to mine a bunch of lithium and things like cobalt, potentially. And then they start to realize batteries can't fix everything. So when it comes to energy storage, we need to be really creative with how we're using it, the different forms we're using it, and recognize that things like thermal storage, or even buildings as batteries, as it's called, can help us supplement the traditional way we think about energy storage, which is chemical batteries. So for example, if the grid is gonna be really heavily loaded in the evening when everybody comes home and turns on their air conditioning and turns on their TV and starts cooking with their induction stoves, maybe we actually pre-cool your house during the times where there's a ton of solar production. We overlap the supply with the demand better, and then we don't have to use as much electricity during the peak periods. So your house has air that can be used as a battery, your water heater has water that can be used as a battery. There's a lot of different forms of energy storage that are also out there in conjunction with everything that we've talked about so far.
Very good. Emma?
Yeah, I want to, so my master's research was on nuclear renewable hybrid energy systems. And so it was on how, okay, now we have a grid that is more fluctuating than it's ever been. So sometimes we have way more power on the grid than we need. And that one way to use that excess power is in things like hydrogen production. And so it's something where, okay, we can have nuclear running and being a consistent power source for those times when you really need reliable energy, and when you have a lot of solar on the grid or a lot of wind on the grid, then you can use that excess energy to do things like metals fabrication or hydrogen production, synthetic fuels production, desalination. I mean, there's a lot of ways that we can use excess energy that isn't just storage in some sort of battery system. Ammonia production, another way of using hydrogen. So yeah, mostly just reiterating what was already said, but yeah, there's great ways to use excess energy for sure.
Very good. So I'm going to divert from my plan just a bit because I want to follow the thread on hydrogen a bit. So hydrogen is its own conversational piece because hydrogen itself it's a material, right? And hydrogen's an atom. And so people talk about hydrogen in two ways. They talk about it as energy storage, and they talk about it as an energy carrier. And so it's a little bit complicated. So I'd like each of you, if you wouldn't mind, to share your perspective on how does hydrogen work. And if we could start, Peter, with how hydrogen's produced today and why green hydrogen's different from that.
Sure. So hydrogen today is made from steam methane reformation, where you take CO2 and you essentially apply a thermal process and you drive out...
You take natural gas.
Oh, I mean natural gas, excuse me, CH4, excuse me. And essentially you separate the hydrogen from the carbon goes off into the atmosphere. In China, they make brown hydrogen, which is with coal, which is twice as carbon intensive as gray. The idea is to take, in today's future world, either make blue hydrogen, which is take the steam methane reformation process, capture the carbon and store it underground permanently. Or green hydrogen, where you take renewables and separate water into hydrogen and oxygen. One challenge, 11 kilograms of water for every kg of hydrogen. So second challenge is you got to have renewables be really, really cheap, maybe $10 to $20 a megawatt hour, and you have to have electrolyzers, and there are 4 technologies, 2 main ones now, high pressure alkaline and PEMs, that are good at dealing with variability. But if you don't utilize those at high capacity factors, the projects become cost prohibitive. It's like a vehicle. You have the car, You have how many miles you drive and the cost of fuel. If you got cheap fuel, but you only drove your car 3 times a year, your cost per mile driven would be really high. So you need cheap renewables, high utilization factors, cheap electrolyzers, which we don't have yet. All those have to combine from that green hydrogen perspective to make this thing cost competitive. I'm a trained economist. That's why I can tell you why the numbers don't yet work.
Great, and so that's a good start to the world of hydrogen. The world of hydrogen is complicated, and there's fossil hydrogen, which we don't like so much for all the reasons. I think you also emit 10 pounds of carbon for every pound of hydrogen you make when you do steam methane reforming. And so there's a lot of carbon that comes just from making the hydrogen that's used today. So how do we think about hydrogen in that context going forward?
There's a lot of research progress being made very rapidly, and there's a lot of research on the development of new catalysts that's going to really reduce the carbon emissions from the SMR technique. This is an example. And Peter is right with regard to hydrogen. We all understand where the challenges lie, and there are really good solutions out there. And so that's why DOE set that goal of $1 per kilogram by 2030. For hydrogen to get the cost done, and it's all the variables in terms of just the capital costs, for example, cheap renewables. All of these things coming together, and there's an enormous progress being made towards that. And so I'm mentioning this because the research progress is fast, the conversation changes as a function of time, and you always want to bear that in mind. Yeah.
Kelly?
Yeah, so not to be too negative about hydrogen. There's actually a lot of hopeful things that are simultaneously happening with advancements in things like electrolyzers or producing green hydrogen. And one of those things is there's certain parts of the country and the world where we have so much excess renewable generation at a given time. So basically what Emma was saying earlier, when we have excess power and we can't send that power through the power lines because they don't have enough capacity or people aren't consuming enough energy at that time, some of it's just curtailed or disconnected or wasted. So to go back to my Hawaii example, Hawaii residential buildings now have these zero export rules. You literally cannot push rooftop solar back. They have enough. They say, please don't give us any more during the middle of the day. We don't want it. Why not use that extra power to do things like run an electrolyzer, split water into hydrogen and oxygen, and then store that hydrogen for long duration storage, which you can then later use in something like a fuel cell. So hydrogen does really address this long-term storage problem, and there's ways that we can more cost-effectively make it. Just in many cases, it's not quite there yet, as Peter said.
And yeah, just to add on, like high temperature steam electrolysis is the path to breaking hydrogen off of water so that you can have clean hydrogen. Of course, high temperature steam electrolysis includes high temperatures, so you need very high temperatures if you're going to do that. You can do that with resistance heating with electricity, but you can also use heat directly. And one thing that's exciting about some advanced nuclear technologies is that they're intentionally very high temperature for these kind of process heat applications. And so yes, you could use excess electricity for this, but also for high temperature gas reactors, molten salt reactors, these kinds of reactors of very high temperature, you can use the heat directly. And that's even more efficient. So you can produce even more hydrogen that we can use for all these different things if we use the heat directly. And you can still generate electricity with that reactor when there's not enough renewables on the grid, and then switch to using heat for hydrogen production.
Yeah, the high temperature electrolysis from nuclear, the low temperature from things you talked about. You get nuclear produces heat. That's just in case, just to clarify that point. Yeah.
Very good. So hydrogen and energy storage have their own conversations, as you can hear. People can make whole careers in each of those. So now we'll shift to some places.
Before, I want to make a point.
Oh,
With
sure,
the hydrogen,
please.
it's really going to be important for decarbonizing the production of steel, for example, and cement. That's another key part of the strategy that we're looking at. It's something with a lot of companies are collaborating on that right now.
So hydrogen has industrial uses, right? People use it, oil companies use it to make their gasoline, for instance. And so hydrogen is needed. And so green hydrogen, just replacing fossil hydrogen in industrial uses, is an important thing all in and of itself, even if it's not used for other things. So green hydrogen production is important. So One of the things that the IPCC and everyone else who studies this decarbonization problem tells us is we need to electrify more things. Things today which we burn fossil fuels to do, we need to electrify. Transportation's probably the key one. And the New York Times has an article today about this. If you haven't read it and you're interested in electrification, it's a very nice explainer piece. But I would like to turn to the panel and say, generally speaking, what do you see as the technology drivers that are going to help us be able to electrify more things? And I'll start with you, Peter, if you could lead us into an electrification conversation.
By way of context, the current administration has set a goal to have a clean electricity grid by 2030. And what this is going to involve is making sure that the sources into the grid are decarbonized, so which means it's going to be a lot of wind and solar, nuclear, and potentially geothermal, but mostly primarily solar and wind are going to be a key part of this. They also want to electrify all the end-use technologies. That's the thought. And so the models of looking at electrifying all the end-use technologies together with sort of the sources coming into the grid being decarbonized is a pathway to get there. And which means then that we're going to have to increase the amount of wind and solar that we're producing right now by huge factors. In some cases, depending on the modeling and the predictions, it could be 5, 8, or 10. If you look at solar, for example, across the globe, we're looking at like 70 terawatts is the best estimate from a group of researchers from around the globe. And so this idea then of electrifying everything in your homes, and you can't electrify everything, right? The long-haul shipping, long-haul airlines, that's not going to happen. Those are going to have to be synthetic fuels eventually, as it turns out. You're going to be thinking about transmission lines as another possibility to make sure that that's there. Nuclear is going to be a part of that solution as well. But there are many pathways and scenarios to get to that goal, depending on how the technologies develop and how quickly they develop.
Very good. Emma, electrification of everything. How is nuclear going to be part of that, and what else do you think?
I mean, I think that Peter covered most of it, but it's that we need to electrify it. Basically everything. It is pretty insane that the electric grid is the easiest thing to decarbonize in a lot of ways. That's why we need to electrify everything, which is wild because that is a very hard problem. And so we're just facing a very challenging problem. Nuclear right now is about 50% of our emissions-free electricity in the country. For the last 40 years, it's been the majority of our emissions-free electricity in the country, so it needs to be part of the overall conversation. Also just noting that, one thing that's exciting to me about advanced reactor technologies is that they are being designed to work well with renewables. So that's, this is, the future is going to be a mix of these clean energy sources.
Let me add something that's really exciting. So she talked about the advanced nuclear, that these small modular reactors are much more safer than the current ones. The modular, you can actually outfit them in abandoned mines. That work is going on right now at Idaho National Lab involving Bill Gates. But the thing that's exciting, a few weeks ago, NREL actually, at the Flatirons site not far from here, they had got all these mega scale wind, solar, electrolyzers, storage, everything's there. And it's connected to nuclear at Idaho National Laboratories. And there's a special ESNet, rapid sort of communication sort of mode involving fiber optics to be able to put together a grid. And so all of a sudden you have this distributed grid with nuclear, and there are us over here with all these devices, and have this thing run to give you a sense of how it's going to work as a test. And so this is the kind of work that's happening right now, for that matter.
Kelly?
Yeah, just a +1 for the small modular reactors. They also consume a lot less water than the larger nuclear plants, which consume a ton of water. So electrification is something essential that we have to do to reduce our carbon emissions and other greenhouse gases. It also has beneficial effects like improving air quality inside your house, improving air quality outside, and in general is something really, really important. However, what we haven't talked about so far is what I foresee as one of the big bottlenecks with the electrification, which is distribution. So the low voltage power lines that take power from those, cylinder transformers on the power poles outside your house or the green boxes in your neighborhood directly into your electricity meter, then into your panel board that's split off into those circuits. So those wires we're not sized for everybody having a Tesla Model 3 or everybody installing all these new electric devices. You might have a 100 amp panel. If you want to install a heat pump with backup resistance, that might be another 60 amps. So we're talking about a huge amount of power locally that's going to be bottlenecked by these wires and transformers that were designed for what the load was 40 years ago. So there needs to be an infrastructure overhaul on the utility end that also needs to happen. And so that's something that things like coordinated charging or coordinated use of your appliances in your house can help with. So not turning on your water heater at the same time you're charging the car, at the same time you're using your induction stove. And ideally, these things should all be automated. You shouldn't go into your house and manually decide when to do all these things. The grid should just know when that transformer is going to be overloaded, because that thing can only supply so much power. And we've seen multiple cases where people electrify a lot, load goes up, in areas that weren't as hot, that are now hotter, people install air conditioners, and those transformers actually pop. They get overloaded and they pop. So a lot of things to think about.
One thing, I have to go back to hydrogen for a second. Law of unintended consequences. Hydrogen, that recent studies have shown, it's a simple atom, right? Or H2 molecule. It can leak. It can get out of everywhere because it's so simple. When it combines in the atmosphere with methane, methane is 80 times more effective at trapping solar radiation than CO2 is. And studies are now showing, and over its lifetime about 20 times, over say 100 years or so, studies are now showing that when hydrogen is released into the atmosphere, it has the pernicious effect of slowing down the natural degradation of CH4 in the atmosphere, thereby accelerating the potential greenhouse gas effect. So we have to be really careful about what we're doing with our future hydrogen infrastructure, and you can't put it in a current gas pipeline because it leaks like everything. Now moving to transmission. There was an interesting study Bloomberg put out a couple weeks ago that said if we want to meet the IPCC goals for the planet, we'll have to double the size of the global transmission system. It would reach from here to the sun, just to give you a sense of the scale on that. And then the last thing, moving to the DER piece of the equation, the distributed energy resources. Our grid today is utilized at 42% of total capacity factor. So if we had airplanes, it would mean that we could all stretch out and sleep most of the times when we fly. That's a really inefficient utilization because we size for a 10-year loss of load probability. So, you know, for peak demand, the hottest days when everybody's using stuff. If we're smart about this and we charge our electric vehicles during the middle of the day, for example, when the sun is shining, we can tummy tuck the duck, right? And we can use vehicles to grid to lop the duck's head off, which isn't quite so beautiful an image, but we can engage a lot of these devices to do better things than they're doing now, but we will have to build not only a more robust infrastructure, we'll have to bring a lot more machine learning to the game. And one last point, I'm sorry I'm going on long, but if we electrify everything, we also have now de-diversified our fuel mixes. Right now we have electric vehicles, we have gas, and if there's an outage, we have multiple resources we can rely on. When everything's electric, and we're trying to supersize the grid, which is already creaky, and we've had outages in California, we'd had a terrible event in Texas, and we were about 4 minutes away from a complete blackout that could have lasted a few weeks. We're putting an awful lot of eggs into the electron basket, and we have to be really thoughtful from a resilience perspective and a risk adversity perspective, especially in a world where there are 13 different persistent threat actors, North Korea, Russia, China, that are trying to hack into our grids all the time. So, again, law of unintended consequences. We have to do this, but we have to be really thoughtful about where we're going and why and the risks we potentially incur. Sorry for the...
Right. Let me add, though, there is what's known as a Grid Modernization Initiative, right, DOE, and it involves most of the national labs. And it's really looking at what is this future grid going to be. And so they're very sophisticated modeling studies looking at using real data from communities to understand what is this infrastructure going to look like for transmission. How much solar and other forms of power generation we're going to need to make this happen. So there's very, very detailed, sophisticated planning being done to address this as well. And so just so you know, there's lots happening. Cyber is a challenge, right? We all know this. And so a lot of labs around the world, including us, working with a lot of industry, using the most sophisticated techniques involving machine learning, et cetera, looking at models to understand how do you detect when something is compromised. So even just yesterday, the last few days, I was talking to a lot of people looking at doing these kinds of things. And so there's an enormous amount of work because the industry is highly motivated because they have the most to lose in a lot of respects. So all of this is happening simultaneously as we get around this. And so the point I made earlier, the advances are quite rapid now. And things that were criticized years ago we're beginning to address. Fast charging, we can charge our cars in minutes. And there's a charging infrastructure that's going to go across the entire U.S. soon. What about the planning is being very careful. Where do you put it? Are you going to have enough power? All of these discussions are going on right now simultaneously. It's a big challenge. It's going to ebb and flow, but we're going to have to get there.
Absolutely, we have to get there. And I will say that what you hear in this discussion here is exactly what has to happen for planning such a complex system, because the bright, shiny, new, cool technologies are all important for decarbonization, but doing it in a way that preserves safety and human health is a big deal too. So I'd like to turn now to the last question that we had talked about before, which is how does this affect me and how can I help whoever me is? So one idea that has come up already is demand response. How do you get homes and businesses to turn down when demand is high? And that obviously is going to come into the customer and affect them in some way. So I would just ask each of the panelists, how's this going to affect the lives of the people in the audience, and how can they help with decarbonization? Okay. And go ahead, yeah. Peter.
So the grid of the future, right, is going to be autonomous, right? Grid of Edison was meant to just generate power, dispatch, no communication. Right now, there's an enormous amount of work going on right where for people. So a typical home is going to have an EV charger, maybe roofed-up solar. You're going to have devices that are communicating. And so you're going to have, for example, a typical home, say San Francisco. You look at about a million homes, round number. Each home may have 5 or 6 devices that are sort of connected. So what you have is millions of devices in a given city. It can no longer be operated by humans. It's going to have to be not done in a way that's using artificial intelligence and a whole range of other sophisticated tools. The simulations being done, NREL, for example, has looked at great detailed simulations of operations of literally every single operating device in a given city to be able to do that. So it's going to be done by machine learning. It's going to be autonomous, not by humans. So that's where we're heading eventually for city by city. And that's already happening in small places right now, for that matter.
Good. Emma, what do you think?
Sure. I mean, in terms of how to support people, one thing we've talked about a little bit here is transmission. And, you know, I do siting work. Siting transmission is incredibly difficult. So one thing to do is basically be a YIMBY, like, yes, in my backyard. So something where, like, if transmission is coming through to support the more dispersed energy sources that we're talking about, solar, wind, small nuclear is going to be more distributed, you need a lot more transmission. And so that means, and so to supporting that, supporting siting all of these different energy technologies, that's something that you can do to kind of help move to this transition.
Yeah, I think probably if you're in this room or on the live stream, you're a step ahead of the average person in terms of educating yourself and learning about the issues and the pros and cons of all these technologies we're talking about. So that's really the first step. When we talk about things like demand response, people changing the way they use energy in response to the needs of the grid, a lot of people don't like that. A lot of people don't like the utility having control over their thermostat or telling them when to use electricity and when not to use electricity, and those are completely fair points. What Peter was talking about, this should be autonomous. It should not be something you even think about. Like, you probably don't know right now exactly when your water heater is on. You just know whether or not you have a hot shower. So this is the way that, you know, loads in your house can shift when they use electricity to help overlap with things like your rooftop solar generation or things like not overloading your distribution transformer. But it requires infrastructure build out, like I said before. So a lot of people in the US still have electricity meters that aren't smart. If you have an outage, the utility has no idea. You might have to manually call Xcel and say, I don't have power. It's kind of ridiculous. The utility should know whether or not you have power. They should be able to send a crew out and optimize this process of restoration, reliability, resiliency. And right now it's just not there. So the first thing we need is basic visibility into grids, basic things like data collection. We can't use machine learning if we don't have data. Machine learning is literally just developing models from data and noticing where there's patterns. A lot of my research is in machine learning for power grids, and I say this, being a researcher in this area, but if you've ever used Microsoft Excel and you fit a line to data points, you have done machine learning. So that line predicts, what the output should be given some input you haven't seen before. That's all it is. It's developing predictions based on data. But we can't do that unless we have the data. So first thing is building the infrastructure, getting people smart meters, educating people, making sure they know what's going on and that the utility's goal is to help them maintain power. And then from there, we can start talking about bigger efforts that consumers can play too. But right now, we just have a problem of, getting the basics down.
So technology is a wonderful thing. And one of you mentioned you have to meet people where they're at. And one of the challenges in the power system is utilities right now and planners are really vertically siloed. So there's the transmission planning group, and then there's the customer focus group, and then there's generation group, et cetera. And when you bring in distributed energy resources, now you're cutting this way. So you have to start to break down the silos, and you have to start iterative planning. If we have this many responsive water heaters, this many EVs that have vehicle to grid and so on, what can we do? So there's a lot of work that needs to be done within utilities. And they also have to be incentivized and compensated for by the rate-making process, which if you know is, right now, if you spend $100 million, you get 8% for spending that money, and you don't get recompensed in many markets if you save money. So we have to change that. But one really bright shining light is a project called the Brooklyn Queens Demand Management Project. This was in Consolidated Edison in New York City area. A bunch of yuppies moved into Brooklyns and Queens, and they party. And so peak demand shifted into the evening from around 7 o'clock to 11 o'clock at night, and it was stressing the grid. So Con Ed said, we're gonna have to build new infrastructure, new substation, the things you drive by with all the big pieces of equipment, and feeder lines. And the cost of that was gonna be $1.2 billion. So Consolidated Edison said, well, let's not raise the bridge, let's lower the river, let's attack demand. And so they put in efficient lighting, which coincided with that period of time. They put in fuel cells. They did demand response and a few other measures like voltage regulation. And instead of spending $1.2 billion, they spent $116.5 million. So a tenth of that. Now, they didn't get their normal rate of return that they would have. They got paid more because they were more efficient, but it was a special case where the regulators were really helping them move through it. But there are some really interesting examples where DERs, distributed energy resources, properly harnessed can create immense value for society, which should accelerate this whole process. But at the end of the day, great tech doesn't go anywhere unless society figures out how to organize around it and adopt it and utilize it.
And to add, with DERs around, there's more opportunity for cyber criminals to attack. So we're also trying to understand how to defend that space as well. So nothing comes free.
Nothing comes free is right. And so with that, we're going to turn into the Q&A. And I'd like to start with a student question that we have, which touches on the other side of the problem, which is how are each of you thinking about the inequalities arisen because of renewable energy siting in areas that are on indigenous lands? And so I'll turn to you, Emma, because you talk about siting as part of your work. And so if you'd launch us into how do we make these changes we need to make in a way that's careful and respectful of the people we impact.
Yeah, a just transition is an incredibly important part of the discussion. It's something where, it's interesting to see that the closer you get to renewable installations, solar and wind, the more anti-solar and wind people tend to be because it impacts their landscape. I think Joshua Tree is a really good example of that story. And so it's something where you have to put these things where people want them to be. That's true also clearly for nuclear. Nuclear is a weird case because the closer you get to a nuclear plant, the more pro-nuclear people tend to be because they know more about the technology. And it also economically benefits the community as a whole quite a bit. There's a lot of good jobs that are associated with nuclear facilities. But it's something where nuclear hasn't historically done a great job of paying attention and listening to where people want things put. That's something that needs to change. That's something that the new generation of nuclear needs to do. That's something that, when we're doing outreach, people need to absolutely listen and do the due diligence of being in the community and reaching out to different groups and hearing what matters to them. Ultimately, we need to put these things somewhere. That's part of the problem, is we do need to put solar, wind, nuclear, clean. If we're gonna make a transition to clean energy, they have to exist in a place. And so making sure that we're paying attention to not putting this just where it affects people who don't have a voice. Because people who, if you're putting it on indigenous lands or more where people are underserved, they don't have the time to go show up to a public meeting and advocate for themselves. So making sure to pay attention to, hey, what are the problems that people are facing in that area? How do we make sure to hear their voice? It's a very challenging problem, and it's not something there's a universal solution to. Every community is unique. So,
Peter.
Yeah. So DOE just implemented a program called Clean Energy to Communities. And the initial investment's about $50 million. It's going to grow significantly. And the idea is that they're going to work with poor communities across the U.S., where experts are going to be working with these communities to understand collaboratively what their clean energy ambitions are, work with them collaboratively to understand what kinds of technologies and infrastructure they would need. So for example, in Alaska, one of the things that we did at NREL was, how do you replace a coal plant with wind? And it involved a very detailed analysis of the grid, how it operates, putting wind turbines, sizing them appropriately, and demonstrating to that community that this is viable and it will work, and it does work. And the plan is to look at community by community across the country with that. And it's not just NREL, it's all the DOE labs working with universities. That's what the plan is going to look like, to ensure that this truly is a just transition. This is really important. I'm not a politician, but this administration is invested an enormous amount of money to try and make that happen. So we're trying to jumpstart that. This idea of the experts coming and telling communities, these are the technologies they use. They've learned that's not happening anymore. The plan is to actually take the time to understand. In Alaska, for example, when they're building homes, instead of putting them on stilts, they're putting them on, for example, on sleds, and putting modular buildings and things that people can actually replenished in sustainable ways. All of this thought is going into things like that, for that matter. So I'm not a part of the administration, but I'm telling you, this is what they're doing. This is, where the efforts are, because people are beginning to get it. The fact that unless it's really just, and unless you're really working with poor communities and looking at the buildings, upgrading the buildings, and you're providing this source of power for them, and you're sort of testing out and proving technologies, this ain't working. Very simple.
Yeah, what was said is a really, really good summary. I would just want to add to that, it's not just access to the technologies that's a problem, but it's, again, to harp on this, the infrastructure itself. If you take a look at a high-income community, they might have underground power lines. They might have really, really nice infrastructure that provides reliable access to power. You take a look at an older neighborhood or a neighborhood that has lower income residents, you see overhead power lines, power poles that haven't been hardened or updated in decades, frequent power outages that aren't restored quickly, and in general, aging infrastructure that's resulting in long power outages. So we also need to not only provide the shiny new technologies, like helping all consumers have benefit and access to things like solar and clean energy technologies, but also the poles and wires, and helping remove inequities from the wires themselves.
In providing access to the clean tech, it's mostly wealthy folks that have solar on their roofs and an EV in the garage. And partly it's because they have a roof, right? And so they can also do the charging at home. People who live in multifamily housing, often lower middle income, where do they charge their vehicles? Where do they get access to solar? How can they participate? Certain things like community solar, where you put 1,000 panels in a field somewhere and everyone has fractional ownership, they help. And the Biden administration is doing a lot to make that happen right now, and it's also trying to address the EV charging deserts around low-income neighborhoods. But up until now, this has been very much a story of tech adoption by folks who can afford it, and those who cannot have generally been left behind. We've got to change that equation.
Very good. Thank you for those thoughtful answers to that. I'm going to have another question, which is somewhat related in a sense, and it's a student question as well. It's what do you think the government should do to address this issue? And I assume the issue here is energy provision and balancing with the concerns of siting. Should the government be involved? So I'll turn to Peter. You're an economist, so I'll start. Or you've got an economic interest. So what's the government role in balancing the needs of the clean energy transition?
Yeah, I think at the highest level, there do need to be economic levers pulled. I mean, transmission siting or plant siting is a classic example. Once you put a facility into an area, a chemical plant or something, you usually put it in there first because the people who live there can't afford to fight you. And then once you put it in, property values go even lower. So then it's easier to put the next thing in and the next thing. They're falling dominoes in the wrong direction. So as we do the siting in the future, we can't just rely on the dollars and cents. We actually, I think, have to put a finger on the economic levers and say, no, we can't just put it here because this is the cheapest path with the least resistance, because that's an inequitable outcome. And I think government has to be proactively involved in trying to change that, whether it's involving subsidies or some other approach. We have to become much more cognizant of what the existing biases are, and then government's changing that.
Very good. Emma, what do you think? How should the government help us through this transition?
I mean, I support what Peter said in making sure that you're providing a space for people in local communities to speak about what they want. It's something where I think all these different technologies need to compete on their own. That's another fair point to make, like wind, solar, nuclear, they all are getting some sort of, the IRA passed and they're getting some sort of production tax credits and things like that. And as things that don't result in climate change and air pollution should. The role of the government is clearly to protect the people, and we have a lot of externalities coming out of fossil fuels that nobody is paying for except for public health right now. And so making sure that the government's appropriate role is to support technologies that help people. So I think that supporting all clean energy technologies makes sense, and making sure that we're doing this in a way that we're putting these where people want them. That's also the responsibility of the technology developers, is to create products that people want and to integrate into the community and make sure people want it there before you put it there.
Very good. So another question that I have that people asked me before the panel as well, but I'll ask it here because I think a lot of people will be interested. So we've seen some big announcements about fusion out of national labs. So I'll turn to our nuclear expert and ask the question, when will fusion ultimately be available?
Yeah, I mean, it's interesting. Yeah, the laser confinement fusion, hitting break even and producing a little bit of power out of Lawrence Livermore was I think the topic. My first interest in nuclear was fusion. So when I was doing this transition from environmental studies to nuclear, and I was like, oh, fusion, it has all these cool things. And I did some research on it, and I decided not to go that route. So I'll just leave that there, I guess. Fission's pretty great. So.
Okay. Anyone, Peter?
Oh, I'd just comment, when I was an undergraduate in the 1970s, it's a fusion in 20 years. But this advance at Lawrence Livermore Labs, you get more power out of what you put into it, is an important advance. And people are very optimistic about that. There's a lot of DOE investment. There's also a lot of private equity investment in fusion right now, by the way. And so, these guys are saying maybe another 20, 30 years. It's not going to be immediate. But it is important to continue the research, because when successful, it's a game changer. It's safe, and you can put it anywhere you like. Okay? And so this is going to be, I think, a game changer in the future. But it's going to be a couple of decades away, not years.
Very good. So technology of the future and always has been is the way I've heard it summarized. So, but I do want to stick with the nuclear theme, because that's a little bit kind of space fiction-y, the fusion side, but fission is not space fiction-y, science fiction-y at all. And so I have a question here. Are you concerned at all that expanding nuclear energy will impact other social issues? And then I have related questions that ask about, can you explain modular nuclear reactors and how that's different with the distribution since they're smaller? So I guess I'd just like to open up a quick discussion of nuclear for the whole panel. We'll start with Emma, but really bring us up to date on where fission is and how might that actually roll out.
Yeah, I work in advanced fission. I do a lot of advocacy work around existing nuclear because existing nuclear power is great. It's here, it's producing clean energy. We should keep it for as long as possible. I am really excited about advanced nuclear for some of the reasons I've already mentioned. They have things like high temperatures. They're able to work really well with renewables. They work with the direction that the grid is going for more distributed. So where advanced nuclear kind of is at right now, there's a lot of companies developing different technologies out there. There's a focus on making it easy to manufacture. So once you get one built, you build a large factory to just put out a bunch of these different modules. They're much simpler designs. They've got a lot of inherent and passive safety characteristics that are really cool. Another thing that I always think is interesting about nuclear is, and we've talked about these new shiny clean energy technologies, a lot of the advanced nuclear stuff's been around for decades. We're talking about stuff that was developed in the 1950s and has had decades of research and commercial operation around the world. We haven't commercially pursued it in this country because large light water reactors have worked great for how the grid was when we were building a lot of nuclear. Yeah, so those are some of the things that I'm excited about. If anybody wants to talk to me more about all the different companies and the different types of tech out there, happy to talk about it. They all kind of serve a different role because you can make this all different kinds of sizes. You can make it different temperature outputs. You can and then of course one thing that I'm really excited about is the commercialization of nuclear waste recycling, and so that's something that at least one company is pursuing, taking our nuclear waste and turning it into clean energy. We have 150 years of clean energy clean electricity for the country in our nuclear waste alone. So that's something that advanced nuclear fission plants can do, fast reactors especially. So that's another note that I think is pretty exciting. I'll leave it open to the rest of the panelists to talk more about.
Yeah, I mean, just for context, this small modular nuclear reactors can fit in the back of a truck, okay? And they're trying to make them cost effective, so when you need electricity is affordable.
Great.
And we sometimes call it a huggable reactor. So it's
Huggable reactor.
It's crazy how much energy density is in nuclear. So we're talking about today's nuclear plants are 3 million times as energy dense as coal, which means you have to do 3 million times less mining. Advanced nuclear is up to 20 million times as energy dense. It's wild, and these things you can put into remote communities for 10 years without refueling. So it's just it's a paradigm shift in how you think about energy. So it's a kind of mind-boggling technology, I think.
Kylie, any thoughts on how nuclear impacts the grid?
Yeah, I mean, first of all, I want to emphasize that diversity of resources is really what we aim for. Like, I do research in renewable energy, and it stresses me out to think about a grid that's 100% wind and solar. Absolutely stresses me out. Nuclear is a great example of a firm energy source that can help provide sort of this base load generation that we need during times when we don't have the transmission to pipe in the wind or the solar, or we just don't have the generation to begin with. I even believe that we should still have a little bit of natural gas peakers. I think a diversity is really, really important, and we shouldn't lose the forest for the trees when we think about we need 100% decarbonization. Getting to that last 10, 20% is just extremely challenging. So we need to think about decarbonizing other sectors, industrial, transportation, these other massive high emission sectors. The grid is one thing. I care a lot about the grid, but it's not the end all be all. We decarbonize the grid, and we've decarbonized everything and solved climate change. So nuclear is a big part of that. I also want to mention something called interconnection queues that we haven't talked about yet. So the amount of installed generation capacity right now in the US grid, the amount of generation that's currently in a queue waiting to be built and put online exceeds the amount that's currently installed in the grid. And that's mostly renewable generation. So there's a ton of companies out there that are just waiting to be approved to start building. So there's not a deficit of people who want to build these renewable projects. It's a complex, extremely lengthy, and extremely complicated process where they have to do an engineering study to see if I connect this wind turbine to the grid, is it going to cause frequency instabilities? And so that process, just going back to the where should government play a part, streamlining interconnection. That's a big place where the government could improve this whole process. Right now, it takes over 10 years on average to put up a new transmission line. We can't wait 10 years to put up a power line. Like, this process really needs to be streamlined. Yeah, I'll leave it. I have a lot more to say, but I'll leave it.
Yeah, the queue right now, if you jump in today, you won't get approved until 2026. About 20% of projects historically in the queue actually go from concept to light of day. And there are a bunch of placeholders in there as well. So it's not like they would all be built, but it's still a huge amount. A couple things on nukes. If we're going to electrify everything, we're going to have to triple the size of today's grid. And doing that with wind and solar alone, I mean, you need raw terawatt hours. You just need to throw a lot of electricity at this problem. And so nukes probably have a pretty significant role. The challenge right now, as an economist, is one of cost. So the most advanced in this country from a permitting perspective is NuScale. They have their NRC, Nuclear Regulatory Commission, design approval. They've had a contract with an association of Western municipal utilities, Utah and some of the states around there, and the original contract price was $58 a megawatt hour, which compares pretty close to what you can do with natural gas today. But they just announced in January that price was bumping up to $89 a megawatt hour, and last month the CEO said that if we can't triple the number of subscribers that are committing to offtake by 2028, 29 when this is built, the project's off the table. So there are some real commercial issues that need to be overcome, and maybe it's government subsidies that help so we can scale and get the volume. There are, however, others, like Dow just announced a 50 megawatt nuclear plant they want to build just for thermal down on the Gulf Coast. So there's interesting lights of potential progress, and every time I get excited, then I see something about a cost or something that makes me go from a smile to a frown, but we need these things to succeed. And so we're going to have to figure out how to do it and scale it and have them see the light of day.
Yeah, that's right. The permitting is the biggest challenge. We have mentioned geothermal. And that community is actually developing technologies over time so they can actually access geothermal across the entire U.S., not just in the West where it's readily available, where you can actually, there's available steam and processing. So if that works, then geothermal will actually provide maybe about 6% of the power, maybe more, a little bit more if I remember the numbers right at some point. So between geothermal and nuclear, providing base power, it could be a game changer in the years to come.
Yeah, geothermal potentially could be limitless. There's a company with a project right now that got $80 million from the EU. They're drilling outside of Munich, using fracking technology, going down, separate pipes, running into each other, and then creating multiples and building a radiator underground. Then they take the heat from the earth, run it through circulating fluid, generate steam, and they have dispatchable power. There's another one that's drilling in Nevada right now. There are dozens of companies in Texas using oil and gas expertise to build geothermal. It doesn't have to be on tectonic plates or where we've traditionally sited it. We're now getting good enough at drilling deep enough into the Earth's crust and harvesting the heat down there that we may be able to cost effectively create generation that actually is dispatchable and can follow our demand. It's really early, but it has a huge amount of potential.
Well, I'm very glad to hear geothermal brought up because one of the governor of Colorado, Jared Polis, is the head of the Western Governors Association, and one of their big pushes in the next few years is called Heat Beneath Our Feet, which is about geothermal energy. And one of the places we might actually see it in Colorado is in the valley where the collegiate peaks are. So there's a group that would like to put in a 10 megawatt geothermal plant a couple of miles from Mount Princeton Hot Springs, which would be enough to power Buena Vista, which is just up the road from it. So the geothermal in Colorado may be happening because our governor is supporting it quite a bit. So there are some questions that we weren't able to get to, and I'm sorry about that. You can come talk to our panelists after the panel is over. One subject area that we didn't touch on, but I'll leave it out there as a seed for conversation, is how's AI going to impact the way that the grid is managed and that the energy system interacts with people. So I'm going to bring this to a close because I have to run off and do another panel immediately after this. So we'll finish right on time. I would very much like to thank our panelists for being here. This was a fantastic conversation. I appreciate what each of you brought to it and your insights. And to the audience, thank you for being interested in such an important topic and something that's going to be relevant to everyone going forward. And so with that, I'm going to say thank you, and everyone have a good rest of your Conference on World Affairs.
Continuing education knows that at the end, students want to graduate, and we can help them do that because we take the time to really listen to their needs and we understand all the different options that are available across the campus for them.
We don't take a cookie cutter approach. We realize each student comes with their own story. So whether it's a part-time student looking to complete a degree program or someone just looking for online courses, we're there to connect them to the resources of the university.